Politehnika Nova Gorica je oktobra letos obeležila prvo desetletje svojega delovanja. Na svečanosti dne 22. oktobra 2005 v Slovenskem narodnem gledališču v Novi Gorici je častni doktorat sprejel profesor dr. Paul Crutzen. Crutzen je bil leta 1995 Nobelov nagrajenec za kemijo. Že dan pred svečano prireditvijo v Novi Gorici pa je profesor dr. Crutzen predaval na dvorcu Zemono pri Vipavi. To je bilo hkrati tudi prvo predavanje v ciklu z naslovom Znanstveni večeri, ki ga organizira Politehnika Nova Gorica in sofinancira Ministrstvo za visoko šolstvo, znanost in tehnologijo v okviru programa promocije znanosti. Dogodek na Zemonu je moderiral profesor dr. Mladen Franko z Politehnike Nova Gorica.
V posebno čast in veliko zadovoljstvo nam je, da vam lahko nocoj predstavimo kot prvega predavatelja v nizu teh predavanj tako uglednega znanstvenika, kot je profesor Paul Crutzen. Profesor Crutzen je diplomiral na visoki šoli za gradbeništvo v Amsterdamu in se po nekaj letih preselil na Švedsko, kjer se je vpisal na podiplomski študij na univerzi v Štokholmu in kmalu z področja meteorologije pridobil magisterij, kasneje tudi doktorat filozofije in leta 1973 doktorat znanosti. Akademska kariera ga je nato vodila preko podiplomskega usposabljanja na Oxfordski univerzi v Združene države Amerike, kjer je delal na uglednih nacionalnih inštitutih. Od tam se je leta 1980 vrnil v Evropo in se zaposlil na inštitutu Max-Planck v Nemčiji, kjer je kasneje vse do upokojitve leta 2000 bil tudi direktor inštituta za kemijo. Kemija je bila, oziroma kemija atmosfere, je bila tudi osrednja področje raziskav profesor Crutzena. Seveda je profesor Crutzen ves čas tudi uspešno publiciral. In za tiste, ki radi merijo uspešnost znanstvenikov po številu citatov in publikacij, naj povem, da je bil za obdobje 1991 do 2001 imenovan kot najbolj citiran avtor v svetovnem merilu za področje geoznanosti. Skoraj 3000 citatov za 110 publikacij je bilo objavljenih v znanstveni literaturi. Profesor Crutzen je danes častni član več akademij znanosti in umetnosti, omenim naj samo ameriško, rusko, švedsko, evropsko. Poleg tega mu je kar 13 univerz podelilo naziv častni doktor. Lahko bi rekli, da je profesor Crutzen posvetil svoje življenjsko delo proučevanju atmosfere in vplivov na njo ter preprečevanju negativnih posledic, ki jih ima na naše okolje ravno delovanje človeka. In to v obdobju, ki ga je sam poimenoval Anthropocene. Kaj več o tem pa naj nam pove profesor Crutzen sam. Profesor Crutzen, the floor is now yours.
Thank you. Thank you, Professor. I was introduced by Professor Franco in a remarkable way. I've never experienced that somebody had all these data in his head, so it was really masterful. But let me introduce myself a little bit. What? Yeah, here. Here I am, with my grandmother. This picture was taken more than 70 years ago. And you see, I was a happy guy. My grandmother was not so happy because just a year before my grandfather had died, so that's why she is dressed in black. So I have changed a lot, but also I'm not the only thing which has changed. No, there are many things which have changed during my lifetime on Earth. And to mention a few examples, during the past 3 centuries, human population has increased tenfold to 6,000 million, 6 billion people, and in the last century by a factor of 4. Cattle population also has increased by roughly a factor of 4. There are now about 1,400 million cattle in the world. That means per family there is one cow supplying us with milk and cheese and steak. So, and by doing that, I mentioned the cattle because the cattle is responsible for production of methane. And methane is an important gas in the Earth's atmosphere, which I will speak about. Urbanization has grown more than tenfold in the past century. Almost half of the people live in cities and megacities, and this trend is continuing. Industrial output increased 40 times during the past century. Energy use 16 times. Almost 50% of the land surface is affected by human activities, and this is again growing. Water use increased 9-fold during the past century to 800 cubic meters of water per capita, 65% of which is used for irrigation, 25% for industry, and 10% for households. Human appropriation of terrestrial net primary productivity, that's basically the photosynthesis process, is about 30% of that is used by humans. Now this number is very uncertain, but it's roughly in that ballpark. Fish catch increased 40 times. The release of sulfur dioxide, SO2, to the atmosphere is about 160 million tons a year by coal and oil burning, and is at least twice the sum of all natural emissions. And if we only consider the emissions over land, then there is about 7-fold increase over land in the release of sulfur species in the atmosphere. And this has caused health effects, acid rain, poor visibility, and has an influence on climate, about which I will speak a little later. Releases of nitric oxide, NO, to the atmosphere from fossil fuels and biomass burning is larger than its natural inputs, causing high surface ozone levels over extensive regions of the globe. This is the photochemical smoke, which you will hear about in summertime especially. And then several climatically important greenhouse gases have substantially increased in the atmosphere. For instance, carbon dioxide by 30% and methane by more than 100%. Humanity is also responsible for the presence of many toxic substances in the environment, and even some which are not toxic at all, but which have nevertheless led to the ozone hole. And here I mean, of course, the chlorofluorocarbon gases, which nowadays are no longer produced, but up to the year 1996 was emitted into the atmosphere. Their photochemical breakdown in the stratosphere gives rise to highly reactive chlorine atoms and chlorine monoxide radicals, which destroy ozone by catalytic reactions. As a consequence, UVB radiation from the sun increases, leading to skin cancer and also effects on the biosphere. Nowadays, the emission, if the natural fixation of nitrogen is of the order of a little above 110 million tons of nitrogen per year. So this is this constant line that hasn't changed very much. What has changed a lot is the input of nitrogen by agricultural activities, by the suppliance of nitrogen fertilizer to soils. Part of this nitrogen, this is causing disturbances in the ecosystems, and part of this nitrogen is also released back into the atmosphere in the form of nitrous oxide, N2O, which has an effect on ozone. Man-caused erosion, crop tillage, land conversion for grazing and construction is 15 times larger than natural erosion. So this is an enormous increase in erosion rates. And at current rates, anthropogenic soil erosion would fill the Grand Canyon in about 50 years. Another thing which mankind has had a large influence on is the species extinction rate. This is nowadays between 100 and 10,000, say average 1,000 times larger than under natural conditions. And then what also is of great importance is that mankind affects evolutionary change in other species, especially in commercially important pest and disease organisms through antibiotica and pesticides. This accelerated evolution costs at least $33 to $50 billion per year in the United States alone. So we have been affecting the environment in major ways. We still are doing it. And for this reason, I propose that we really have started a new geological era, which I have called the Anthropocene, the human-dominated geological period, which we are now part of. Now, in this graph, I show you a number of figures. In the upper part, I show you the increase in carbon dioxide in the atmosphere. Measurements, high-quality measurements are available since the end of the 1950s, from a mountain station in Hawaii, Mauna Loa Station. And we see here that there has been a steady rise in the amount of carbon dioxide in the atmosphere over the years. You also see the wiggles. This is the interannual, the seasonal variation in the uptake and release of carbon dioxide by the biosphere. The person who made these measurements, David Keeling, is unfortunately died 4 months ago, but his work will, of course, be continued. He was a real great pioneer. Another thing which has changed in the atmosphere is the ozone, especially at high latitudes in the southern hemisphere over Antarctica. There has been a very rapid decline in the column ozone in the atmosphere. So nowadays we have half to 1/3 of the original amount of ozone in the stratosphere over the Antarctic in the month of October. The month of October is a spring month over Antarctica. And where does this decline of ozone take place? Well, if we look in vertical direction with height, we see that exactly in the places where we normally have a maximum in ozone concentrations in the atmosphere, between about 12 and 22 kilometers in the atmosphere. Just there, this maximum in ozone has been converted into a minimum. This is what we call the ozone hole. And this ozone hole was not expected by any scientist. It was unpredicted, one can say also unpredictable, because there are many factors which come together, which all look very unlikely, but they together have caused this ozone hole. What you need to cause this ozone hole, and this was found by research carried out in the 1970s and 80s, what you need is sunlight. That's why it has to be springtime or summertime, but it also has to be cold, because under cold conditions, ice particles are formed in the stratosphere, and on the surface of these ice particles, chlorine compounds, which normally do not destroy ozone, chlorine compounds are released in the atmosphere by reactions on the ice particles, which then produce chlorine atom and chlorine monoxide radicals, which very rapidly destroy ozone. So you need all these conditions, and it was, for that reason, it was not seen as very likely. But this shows you something, namely, we never know where there are the surprises. Even if we talk about the climate system, a very complicated system, there's nothing which can tell us that there wouldn't be surprises in that case either. I want to show you a little bit about, talk a little bit about climate issue, and show you the distribution of solar energy coming down on the Earth on average is 340 watt per square meter. Let's call that 100 units. Of these 100 units, about 30 or 28, we don't know too well, units are reflected back to space. This is because of the presence of clouds in the atmosphere, but also snow cover. So the radiation is scattered back to space. That's these 28 units. In the atmosphere, we have absorption of solar radiation. Altogether, what arises at the Earth's surface is 47 units of these initially 100 units. Now, these 47 units of energy, the Earth has to get rid of, because otherwise it would heat up very quickly and we wouldn't be here. So these 47 units the Earth has to get solar energy, the Earth has to get rid of. And let us now look how it does it. That is represented in this part of this view graph. Firstly, there are 24 units which escape from the Earth into the atmosphere in the form of latent heat. Evaporation of water at the Earth's surface and condensation in the atmosphere. That cools the Earth's surface and warms the atmosphere. There's also transport of 5 units of simple heat conduction into the atmosphere. So that is, together makes 29 units. The Earth's surface once has to get rid of 47 units. So there are 18 units left. Now look how the Earth does it now. 18 units in netto escapes from the Earth's surface. However, in practice, what happens is that 114 units escape from the Earth's surface into the atmosphere, of which 96 units are returned. So we have a fantastic recycling of energy by a factor of 6 or 7. That initial energy, that little amount which reaches the Earth's surface, is recycled 6 to 7 times. And that keeps the Earth warm. That is done by the greenhouse gases. Water vapor, carbon dioxide, methane, ozone, and N2O, and a number of other gases. They do the job. So you expect, because these gases are increasing in the atmosphere, you expect that it gets warmer on Earth. But there are other factors. In this view graph, I show again the greenhouse gases, which together, if we add ozone in here, is responsible for additional heating compared to pre-industrial conditions by about 27 watt per square meter. But that's not the whole story. This heats the atmosphere. But there are also things which cool the atmosphere, and these things are particles. In the atmosphere, you see it on the conditions when you have heavy air pollution, you see this haze in the atmosphere. And that means that solar radiation is backscattered to space. And this is done by particles in the atmosphere, which, for instance, sulfate particles, organics, particles which come from simply burning of biomass. And there's another factor which one has to consider, that these particles also are cloud condensation nuclei. Without these particles, cloud formation would be very much suppressed. But because they are in the atmosphere, they help to form clouds that increases the Earth's albedo, and also the clouds will be longer lived. Because if you have clouds with many small droplets, they don't rain out very easily. They sort of hang around, they stay in the atmosphere. And that leads to increased return of solar radiation into space. So these factors cool the atmosphere. And how much, we don't know. We don't know that very well. So it may be that at the present, most of the infrared heating of the atmosphere by the greenhouse gases is compensated for by the backscattering of solar radiation to Earth. And we don't know that very well. But we can make one assumption, namely that the relative humidity in the atmosphere stays constant. If we do that, we can make an estimate. Now, what that is really saying, that if it gets warmer at the Earth's surface, then more water vapor gets into the atmosphere, and that heats the atmosphere. So if you make that assumption, that the that the relative humidity stays constant, then we can do a balance sheet. The greenhouse forcing since pre-industrial times is about 2.7 watt per square meter. Heating of this in energy, additional energy, 0.3 watt per square meter goes into the oceans. So they warm up. There is, and this is the assumption of, which I said already, of constant relative humidity. If you make that assumption, then because the Earth is warming up, there is more emission of infrared radiation, heat radiation to space. And that can be estimated then as 1 watt per square meter. But what we have to get rid of is 2.7. Here we have 0.3. Here we have 1. There's still 1.4 watt per square meter left to get rid of. And this is, under this assumption, is the increased albedo of the Earth, which comes about because of the presence of particles in the atmosphere. And these particles are basically is air pollution. So if in the future we clean up, we take out the air pollution in the atmosphere, we pay it with a price. It gets warmer. The climate heating is going up. So this is a real dilemma we have to face. And it only strengthens the case for more control on the emissions of greenhouse gases in the atmosphere. What I also wanted to point out is that the release of heat into the atmosphere by all combustion processes we as human beings do, the energy of that is only 0.025 watt per square meter. That's only 1% of the heating which comes about because of the presence of the greenhouse gases in the atmosphere. So if we could produce energy without producing the greenhouse gases, we only have 1% of the climate effect. So the real problem is how can we supply energy in the future without emission of greenhouse gases. So if we succeed in that, then we heat the atmosphere by only 1% compared with the greenhouse warming. So that's what we should be aiming for. If that happens, of course, we have no climate problem. Now we want to understand and make even some projections or predictions of what will happen in the future. And the only way of doing that is build models. Now these models are extremely complicated. There are many feedbacks. Many of them have to do with water in the atmosphere, with the latent heat flux, soil moisture, precipitation, and also surface vapor pressure, the amount of water vapor in the atmosphere. Relative humidity, whether it will go up, will go down, or may it be the same as we did the assumption in the former picture. So all these factors are built into the models, and we don't know them all very well. So the models are very uncertain in their predictions or projections about the future. But nevertheless, if we take the best available knowledge, we can make a number of conclusions. And this was done by the Intergovernmental Panel for Climate Change. This in the year 2001. This is a combination of most climate researchers in the world, and what they, the conclusions in the report of the year 2001 was there is new and stronger evidence that most of the warming observed over the past 50 years is attributable to human activities. That we are responsible for the rise in, mostly responsible for the rise in temperatures over the Earth, which has been about 0.6 to 0.7 degrees Celsius since pre-industrial times. So maybe half of that was due for the most recent temperature increases. And now we have seen in the last 15 years that the increase of temperatures has been speeding up in the last 15 years. And what are the projections in the future? Well, the projection is that the global temperature rise in this century, the current century, will be between 1.4 and 5.8 degrees Celsius. Very uncertain, but somewhere in this range. Even the lower number here, 1.4 degrees Celsius, If we add to that the warming we already have had since pre-industrial times, that makes 2 degrees. That's a large warming rate. That could, if it's sustained over several centuries, could lead to the melting of the Greenland ice, and with that, a rise in sea level by 7 meters. That's not very healthy. So that's, if we only consider this century, then we have a sea level rise which may approach 1 meter. But again, the uncertainties are large. There will be redistribution of precipitation. That will be the most difficult to predict. There will be enhanced risk for extreme weather, flooding and desertification. We may see the beginnings of that in the Atlantic, the heavy storms, which there's another one which is coming to hit probably the south coast of Florida. Increase in heat waves in Europe, as in the year 2003. This is predicted by models. And in general, too rapid climate changes is a problem because ecosystems may not be able to adapt to the changes. So what should we do about it? I already mentioned we should put all our efforts into reducing the release of the greenhouse gases in the atmosphere. And of course, in the first place, carbon dioxide. But to do that, in order to reach a stabilization of the methane or the CO2 concentration in the atmosphere, we would have to reduce the current emissions by mankind by more than 60%. So that looks incredibly difficult, and it's not at all certain that we will be able to do that in the foreseeable time. But there are possibilities if we put all our efforts on it. There's methane. There we have a little bit of relief because the amount of methane in the atmosphere is at the moment not increasing. We have had, since pre-industrial time, more than a factor of 2 to 3 times fold increase of methane in the atmosphere, but now it has stopped. And that means that the sources and the sinks for methane in the atmosphere are about in balance. That doesn't mean that it will always be the case, because if it gets warmer, then the permafrost regions in Siberia, for instance, may melt. And if that is the case, then more carbon dioxide and maybe methane will get into the atmosphere. Nitrous oxide, it's also a greenhouse gas. In order to stabilize the amount of nitrous oxide in the atmosphere, we would have to reduce the input by 70 to 80%. And this has to do with the appliance of nitrogen fertilizer to the atmosphere to increase agricultural productivity. So that will be a very difficult task. And then we have the emissions of CFCs. There we have seen that actually the reduction, no longer emissions of CFCs. That is now the case. We have no longer an input of the CFC gases in the atmosphere. So slowly the ozone hole will disappear, but it will take until the middle of this century before this will be the case, maybe even somewhat later. Because the lifetime of these gases in the atmosphere is very long. They hang around for 50 to 100 years. So which are the countries how are the emissions of carbon dioxide in the atmosphere, here expressed in metric tons of carbon dioxide per year? You see the leading countries are North America, the United States in the first place, with a per head consumption of emission of carbon dioxide in the atmosphere by 20 metric ton, and a ton is 10,000 kilograms. That's a lot. Oceania, that's Australia, is adding a lot. Europe is adding a little less than half, or per capita, a little less than half of the CO2 in the atmosphere as North America, Central America. We see then here we have the inputs by the Asian countries. And they will not be satisfied with staying here. That's where we see nowadays the largest input of carbon dioxide in the atmosphere. Because Asia and especially China and India are developing very rapidly. So they will go up. If we don't come down all these, then we have a worsening climate problem, of course. We should not believe that nature comes to our rescue. We cannot believe that if temperatures increase, temperatures increases in the atmosphere, that nature will counteract this in some way. No, the opposite is the case. Whenever temperatures rise in the atmosphere, and here are data of temperatures over the last 150,000 years, and they are now available up to about 1 million years, but the picture is always the same. If temperatures in the ice cores, measured in the ice cores by isotope proxies, whenever temperatures went up, also the amount of carbon dioxide went up and the amount of methane went up. So the greenhouse gases aren't helping us. They are worsening the problem. So how stable is our climate? Well, I don't think it is as unstable as pictured by this caricature, by these symbols. Neither is it as stable as here, because otherwise we would never have an ice age. Now we are somewhere in the middle of these possibilities, and we really don't know very well. Big changes are especially expected in high northern latitudes, also in southern latitudes, but especially in northern latitudes. Temperature rises for a doubling of the amount of carbon dioxide in the atmosphere can be of the order of 4 degrees or up to 8 degrees Celsius at the end of this, for a doubling of carbon dioxide. So that will be, the risk here is, of course, that it will lead to melting of permafrost, more release of CO2 and methane into the atmosphere, and also warming of the ocean surface waters, which then can have an effect on the thermohaline circulation, or in other words, the Gulf Stream. I come back to that. So we expect the largest changes to occur at high northern latitudes. And this is what some of the recent studies say. New studies indicate that the Arctic Ocean's ice cover is about 40% thinner now than 20 to 40 years ago. So it may actually disappear, the ice cover over the Arctic. There's dramatic climate change happening in the Arctic, about 2 to 3 times the pace for the whole globe. And this is the chairman of the Arctic Climate Impact Assessment report says. There are other things we have to, unfortunately, to worry about, and that is one of the results of the input of CO2 in the atmosphere is that it will be taken up, part of it, by the ocean surface. In the ocean surface, and that will lead to an increase in acidity of the ocean surface. And that in turn can lead to a change or a decline in the, I think this went out of business, no. This can lead to a decline in the population of calcifying organisms, which then will have a direct effect on high latitude ecosystems. This is a very recent report which came out about a month ago in an article in the scientific journal Science. So if this is happening, then besides temperature rises, we have to worry about the biology of the ocean surfaces. There may be changes in the thermohaline circulation. This is depicted in this curve. Nowadays, we have a flow of surface waters, of ocean surface water to the north over the Atlantic. By doing this, the ocean surface waters get saltier, and they also get warmer. No, they get saltier and they cool. However, if in future this may change because of the release or the melting of the ice will lead to a lighter decrease in the heaviness of the Atlantic waters, and also less saltier, and that means that the downward sinking of the Atlantic Ocean circulation may stop and in fact may shift to lower latitudes. This is a slight possibility. Some model results predict it, but most models don't see this effect. But I showed you that we have to be aware of that. Maybe surprising things might happen. So while the whole world cools down, warms up, maybe Northern Europe will cool down. It's a crazy situation. It's not totally impossible. I would like to say a little more about the tropics. We should not believe that air pollution is only something which comes from industry. No, air pollution can come from the burning of biomass and forest fires. And of course, in this case, we have the burning of tropical forest, which is taking place, especially now in the Amazon region. Now, there's an effect. What I show you here is air pollution. We made a flight, this is a few years ago, 4 years ago, along the Himalaya range. And here we see Mount Everest. But what interested us as atmospheric scientists more is what we saw below us. Namely, you see this brown cloud. This is what we call the Asian brown cloud. And this Asian brown cloud is not only found near the bottom of the Himalayas. In the dry season, you find it everywhere in the Indian subcontinent and also in Southeast Asia. You see it also in the Maldives. You would think that the Maldives is a very clean environment, but it is in the dry season very much affected by pollution, biomass burning, and also industrial activities over India. So you see, I hope you can see it, but there is this brown haze. We call it the Asian brown cloud, which has a large influence on the radiation budget of the atmosphere over Asia. It's not only, you don't see this brown cloud only over Asia. You see it also over Africa, South America, but it's most pronounced at the moment in Asia, Southeast Asia. Now, this brown cloud is caused by the presence of particles in the atmosphere. And one, you see sulfate from air pollution, organics from air pollution, ammonia from agriculture, and then we have natural emissions of sea salt, and we have dust and ash in the atmosphere. But we see one component here, and that is black carbon. Black carbon, we call it black carbon, it's basically soot. It's the dark matter which comes into the atmosphere by the burning of fossil fuels and also biomass. And black carbon is of special importance because it absorbs solar energy. So the solar energy is trapped in the atmosphere and less of it comes down to the Earth's surface. And that will lead to special conditions which we are now studying, what it might mean, for instance, to the Asian monsoon region. Here we have the additional heating, which is brought about by the presence of the soot particles in the atmosphere, the radiative forcing, we call it, in watt per square meter. And we see that, and we have latitude here, so we here are basically still in the southern hemisphere. There's some pollution there, but then we see the pollution rising, and with that, the absorption of solar radiation within the atmosphere, which heats the atmosphere, of course, and cools the Earth's surface. So we get a situation here in which the atmosphere gets warmer, the Earth's surface gets cooler, and we know from all our knowledge of meteorology that this will lead to a suppression of precipitation. And of course, precipitation is important for supplying the countries in Africa with water for the long dry season. You see also that the regional heating over large areas of the globe, the heating and the cooling is of the order of 30 watt per square meter. That is about 10 times larger than the average global heating of the Earth. So regionally, we can disturb the radiation of the balance by a factor of 10 times more than we disturbed the radiation balance of the entire Earth. So this is something which we are working on in the research program. So the population growth, we are especially interested in what will be happening now in Asia. Already since a long time, the population in Asia has been larger, that's here, has been larger than in the rest of the world, and this is increasing. And on top of that, people in Asia are working very hard on developing, industrialization. Don't have to convince you of that. You see it constantly in the press. And so the question is what the influence of the changes which are happening in Asia will have on global climate, regional and global climate. So where are we going? Are we going into a situation in which we don't find our way around? See here these poor people. Are we changing the ecosystem so much so that we don't know in the future what we should do? I don't know. Let's not, this is of course a caricature, but it sort of depicts a dilemma we are in for. Well, he might know. This is my grandson. Because all these things I'm talking about, the main effects of that will be felt by him, not by me. I mean, I will be gone by then. But in 50 or up to 50 or 100 years, the climate will have changed. And how much and in what way, we simply don't know very well at the moment. But we are doing something to our environment, which we better take care of and make sure that things don't get too much out of hand. And let's hope that this generation will have a future. Thank you very much for your attention.
Thank you very much for this wonderful lecture. As you might know, the series of these scientific evenings is primarily dedicated to the promotion of science in our society. We are feeling that science does not have the, let's say, the role or the image in the society that it should have. What is your impression about the status and the reputation of science in the modern society?
Well, I think it is mixed. I would, for a while, it was very difficult for young people to come into science. I don't know how the situation was in Slovenia, but the number of students at the universities were dropping off very, very rapidly, about reaching a minimum about a number of years ago, 3 or 4 years ago. It's picking up again, but there was resistance for young people to go into science. I think this is changing again, that we have now much more interest by young people to get into scientific fields. Now, science, science has brought us many good things. Our life expectancy is much larger than it has ever been in the past. Medical sciences have done wonders, and diseases have been controlled. So we can move very quickly from one place to another. There are lots of wonderful things we have achieved with science, but we also, of course, have produced an atom bomb and weapons which nature never would have produced. So that I can well understand when people say let's stop doing science. On the other hand, I think we cannot. I mean, our brain is just so constructed that we have to discover new things. And then the question is, what do we do with these new things? And then the politics and society gets in. Of course, as scientists, we may be able to warn for the consequences of what we do, but it's not always clear that what will be the consequences. So, in that case, but in any case, at the end, everybody decides what to do with the scientific innovations. And I don't think it is possible to forbid doing science. I mean, it's so against our nature. I mean, humankind is such that it has to invent new things. Otherwise, it's not very happy.
So, according to you, there is future in science, at least from the growth of young people.
Oh yes, I definitely think so. But in my particular field, in atmospheric sciences, of course, we have these difficult problems with understanding our climate, and we need brilliant young people to develop this science. It's very complicated, but the more complicated, the brighter the brains will have to be who solve these problems. And so there's lots of room for young people here.
We can read from your autobiography, from your CV, that your career was very, let's say, diverse, very interesting. You started as a civil engineer, and then you ended up in meteorology and chemistry, basically. Yeah. What in science has attracted your attention, and what were the motives for which you have decided to be a scientist, let's say?
Well, actually in my life I've had 5 professions, and I had to learn 5 languages. But what got me into science was basically, I got a little angry. I was a programmer at the University of Stockholm, and then one of the tasks I got one time was to help an American scientist with writing a computer program for the ozone layer in the atmosphere. And I started reading the literature, and then discovered that what people were saying was old wisdom, was something which was invented already in 1930, and we are talking here when I was writing this program was in about 1970. I suddenly realized that people were just repeating what somebody had said in 1930, which was okay, but it was not the full truth, and I discovered this. And then I got hooked, and I wanted to find out what was really happening with the ozone layer, and helped develop the scientific story about ozone. I could not predict at that time that ozone could be influenced by human activities, but when I got involved in the science, I started realizing, but nitrogen oxides, they control the amount of ozone in the atmosphere. If we increase the aircraft in the stratosphere, this was around 1970, we get more nitrogen oxides in the atmosphere and less ozone. So immediately after I made a scientific discovery, it had an application, but in the right direction, namely saying we should not build these large fleets of supersonic aircraft. We can't do that because we harm the ozone layer. And partially because of that, these fleets of supersonic aircraft were not built. It was for economic reasons, it was another reason, but on top of that we had a scientific reason.
And you continued all the way to the Nobel Prize, and I assume you did not stop there.
No, I'm still active. But I showed you one of the projects is really finding out what will happen because of the air pollution in Asia. I'm not doing this to point fingers at people in Asia and Southeast Asia. I really do it because it's important, and we have convinced quite many scientists from these countries that this is an important study, and that we, in order to understand the future, we have especially to understand what is happening in Asia.
But a Nobel Prize is definitely something that, let's say, the top achievement, at least considered in the scientific society. We could compare it with, I don't know, winning an Olympic Games medal for sportsmen. And that definitely must have an impact on your personal life. How did it affect your personal life and the scientific life on the other side?
Well, scientific life has changed in such a way that I have less time for science.
More money, but less time.
Sometimes people joke, they say that this is all done because they want to get you out of science. So that's, but in a personal way, of course, there is more pressure on me to come and give lectures and so on. But on the other hand, you also meet very interesting people. You get inspiration in ways which otherwise would not be the case. I've met really wonderful people in all these years who probably otherwise I would not have met. And also important people, not always nice people, but...
So that's definitely a payback from the science, which a scientist could enjoy, and perhaps we can advertise it to the young generation that it's not always money, but there is something more that science can give.
Yeah, and of course, a Nobel Prize is such a rare thing, and there are many, like in my field, atmospheric sciences, and also in general in the environmental sciences, there are wonderful and very important achievements reached by colleagues, and they are not rewarded with the Nobel Prize. I hope this will change. I mean, I hope one time in the future there will be a Nobel Prize for environment, but it's not there. But it certainly would be very important to have one. So.
Well, we who work in the field of environmental sciences say that there are many Nobel Prizes for environment, because environment is such an interdisciplinary field that physics, chemistry, everything fits into the environment.
Yeah, but
let's perhaps go back to the subject of your lecture. Most of your research, at least the research that you were awarded the Nobel Prize for, it was dedicated to the ozone hole. And according to the predictions, the ozone hole should start declining at around the year 2000. And this was happening. But lately, for the last 2 years perhaps, we have observed again the expansion of the ozone hole. And it was explained by the cooling of higher stratosphere. Could you give us a little bit more information on that?
Well, we are on the right way. Within the future, the ozone hole will disappear. We are not quite sure when it will be, but it's around the middle of this century. Now, before that, there will be conditions, meteorological conditions in the stratosphere, which leads to more ice particle formation. And if that happens, low temperatures, then if that happens, then there can be individual years in which the ozone hole will grow again. But on the whole, you will see a downward trend with big wiggles around it. So for the coming 10 years, we still will have years with very heavy ozone loss. I also would like to correct you a little bit. I have been working on explaining the ozone hole, the formation of particles. But it's not the only thing I've worked on before, because the ozone hole issue came about around 1986, while the earlier work I actually got a Nobel Prize for. It was from 1970.
Okay, so I think we should also give some time for questions from the audience.
A few times you mentioned the uncertainty in future climate change, and on one hand we have this big uncertainty, and on the other hand we already have observations that show that climate change is a serious problem. So if we want to act for the future, this is a long-term problem, and we know that politicians have short-term mandates.
Yeah.
They usually don't care much about the problem. So where do you see the solution, how we can raise this awareness about the problem of climate change and how we can contribute to the solution?
The solution lies in better technology. And I think those companies which will use the least energy to produce what they do will be in charge in the future. So if we simply have to put a price on the environment. When we destroy, when a factory or an activity has a negative effect on the environment, then they should pay for it. And if that is done, the pocket money is always a very strong argument. So better technology is absolutely the solution, and development of alternative energy.
What would you give to the Slovene government for what should be done? Shall we support solar energy? Shall we keep Krško, the nuclear power plant, running? Shall be some support for house insulation? What would be the things which can be supported by regulations by the government?
I think we should, there is not only one solution, there is a combination of solutions we should aim for. And solar energy and wind energy is one of them. Whether in the future, again, nuclear energy will become palatable depends on the countries. There are some countries which have no problems with nuclear energy, like Finland, France. Finland is building new nuclear energy plants. Germany is strong at the moment, strongly against it, and basically, for the next foreseeable future, there is no market for nuclear energy. But this differs from country to country. The big problem with nuclear energy is where to dump the stuff, and I don't think Slovenia maybe has very good places where you can get rid of this stuff, because you have a very unstable ground here. So it totally depends on the situation, but in general, one thing you can always say is if you should develop programs to get away from fossil fuel use into other alternative energy uses. And then whether that will be nuclear or not will be very different from country to country, and the attitude of people to it. We should also be aware that we are not at the end of technological developments in nuclear energy. There may be additional developments which makes it much more favorable in the minds of people, and then there will be a resurrection. Then we have, if fusion energy would be reality in the future, then of course we really have paradise on Earth. I mean, we have unlimited amount of solar energy. We would not have of energy. We would not have to build. We would not have to burn fossil fuels. So in general, we would have paradise on Earth. But that sounds too good to be true, really.
I'm an economist, and I am very honored to have a question for a man who have a Nobel Prize. And I would like to ask you, we have on the other one side the scientists, on the other hand the politicians, and the third side it's the economy and the economists. Is it possible that in one day or in the near future these three parts will take together and to take very seriously this problem? Because we are all agree with you have told us, but that it's a very big problem to find compromise between these three parts.
Yeah,
Thank you.
Mm-hmm. You asked me a question which is very difficult to answer, but of course they have to get together. Economists, many economists don't see this as a very difficult problem, because economy and in general will in some way get rid of this problem. But many of them make a mistake, and that is not counting the cost of destroying nature. Because if you fold that in, the price of that, into the thinking and into the models of economists, many kinds of economists, then if that would change, then I think we could better talk with each other. So we should put a price on nature. At the moment we are, it's said that it's called oil production. You know, you look at the statistics and you see that oil companies call the use of oil as oil production. I would say it's called oil destruction, because you take out something which nature has produced for you, and you shouldn't take it out as quickly as we are doing. So, but all these forces have to come together. The only thing I fear is that they first come together when it is too late. But so then we have to be aware of these problems. And one important thing is that the science we are doing should be as good as possible. There are, of course, many uncertainties, but your political attitude should not influence your scientific results. I mean, the integrity of the scientific method should be retained. Otherwise, if that doesn't work, then nothing works.
So do you think that it's okay for the environment that the oil prices are going up?
I think it's a good thing, yes. I have a few stocks in the stock market, so maybe they will go down. But on the whole, I think it's a good thing, because you start thinking about these things, and maybe you let your car unused, or you even get rid of your car. I mean, I don't have a car. Since 15 years I don't have a car, and I'm perfectly happy without a car.
Okay, I think we came to the point, Professor Crutzen, where we should thank you for the wonderful evening we were privileged to share with you. Thank you very much.
Oh, thank you very much.